I'm starting that now. So apologies to the several people who are not here right now. Please do not hesitate to remind me, because it is my intention to start recording as soon as possible once class starts. So yeah, I was lucky enough to not forget last week, but it does happen. So I don't care if 10 of you want to remind me. It is very important that someone does, just in case. It's been a day, I'll put it that way. So thank you for Paul for posing that question. Okay. So for those of you who are tuning into the video, unfortunately, the first 7 minutes were not recorded. So all I did during that time was go through these problems of writing vector equation as a system of equations in the first problem, and then doing the reverse, given a system of equations, write it as a vector equation. So it just changes the notation. So fortunately, the more involved problems, at least, will be in this recording. So again, my apologies for that. Okay. Now, going to the next. Okay. All right. So here, in this problem, you're given 3 vectors, and what you're asked is this vector a linear combination of these 3? Now at this point, this is the first problem that explicitly mentions linear combination. I have it queued up here to give the formal definition.
Dr. Lambers, did you mute yourself?
Okay, like I said, it's been a day. I did not knowingly mute myself. Can anyone tell me what was the last thing they heard me say?
What was the formal definition of a linear combination?
I'm sorry, could you repeat, please?
You said you were about to give the formal definition of a linear combination.
Okay, so at least not much was missed. I seriously do not know how that happened. What I could have hit that made me mute myself, because I've been in this document the whole time. Okay, so anyway, all I was doing while you could not hear me was just go through this definition. So, and I think a point I was making that was not written down is that so here when I'm taking these vectors, multiplying them by these numbers, and I call these numbers scalars because they're literally scaling each one of these vectors. But we might also refer to them as just constants or coefficients, something of that nature. But we're taking these vectors, multiplying by these numbers. In other words, we're scaling of vectors by these numbers, adding them up. That's a linear combination, and something that is one of the most important concepts we deal with all semester long. So it's very important that this stick with you. Okay. So if I take a linear combination of these vectors and set them equal to this vector b, what the question that this problem is posing is, is it possible to take these vectors, multiply them by any scalars, x1, x2, x3, and actually obtain B? Now, what I can do is, what we have here is a vector equation, like we saw in the previous two problems. So now I could write that as a system of equations also. So what I have here, if I look at this row by row, I'm saying x1 times 1 plus 4 times x3 is equal to 2. And then similarly for second row, third row, that gives me these equations here. Now, in order to determine whether it is possible to take a linear combination of these three column vectors and get this vector, that's the same as checking whether this system of equations has a solution at all. Now, how can I check if a system of linear equations like this one has a solution? I can look at the augmented matrix. So if I go from here, and this is why it's a good idea to be able to go back and forth between vector equations and system of equations. Here I can get the augmented matrix. Okay, so here we have all the coefficients in the first three columns. The right side goes into the fourth column. Now, what I've done so far is I took these vectors, and because it's asking if this vector B is a linear combination of these, I wrote out this vector equation with unknowns x1, x2, x3. I wrote it as a system of equations, and then from there wrote down the augmented matrix. Now, that intermediate step here is not necessary. We could go directly from here down to the augmented matrix, because each one of these vectors, A1, A2, A3, fill a column, and B fills a column. So I could take A1, A2, A3, and B and just slap them together in this matrix, one column each, and that's my augmented matrix. So then what I'm going to do is I need to use this augmented matrix to find out is it consistent? So to find out, I'm going to do what I've done last week, row operations. So for example, here, I'm going to take the second row and subtract from it -2 times the first row. So in other words, row 2 is itself plus twice R1. So that would cancel out the -2 and 2. So I'm going to eliminate this element. And what that gives me is this element zeroed out. But now I need to zero out this element also as part of getting my echelon form. So row 3 will be equal to itself minus twice this row to eliminate this 2. What we get here is so the last row is entirely zeros. Now, okay. So we at least see that the system is consistent. Like if I had 0, 0, 0, and something non-zero here, that would be an inconsistent system, and I could let's say that B is not a linear combination of A1, A2, A3. But the system is consistent. Okay. In fact, because we have this row of zeros, there's actually infinitely many ways to combine A1, A2, and A3 to get B. So if we go back to the vector equation, x3 does not correspond to any pivot position. We only have a pivot position in the first column and the second column. We don't have a pivot position in the third column. So x3 is a free variable. I could ignore it. I could set it to 0 if I want, and just use x1 and x2 to get B. So in the 1, 1, and 2, 2 positions are where we have what are called pivot positions. So it's the first non-zero entry in each row. So since we started with the question of whether a certain given vector B is a linear combination of A1, A2, A3, but we wound up working with an augmented matrix, I'm going to lay out for you explicitly certain statements that are equivalent to one another. So if you recognize an equivalence, that helps you take whatever question is actually posed to you and transform that into a form that you can work with and actually answer the original question. I find myself paranoid, wondering if I've accidentally muted myself again. Okay, so the first statement would be that a vector B is a linear combination of A2. Now, in this problem, we had 3 vectors, but it could be any number of vectors. All right, so let's say if we assume we have P vectors altogether. Another way of saying this is B is in the span of these vectors, A1, A2, and so forth. All right. The span of a set of vectors is the set of all linear combinations of those vectors. So I can multiply these vectors by literally any number whatsoever, and that's a vector in this set. Okay, now, so those 2 statements are equivalent. What else do we have? So the vector equation I multiply these vectors by scalars equals B has a solution. Now, it may be a unique solution, or it could be infinitely many solutions like it was in this case. But the point is, there's at least a solution. That's the same as saying so the system of equations AX is equal to B is consistent where A has these vectors, A1, A2, etc. as its columns. Okay. What we could also say is the augmented matrix that we get from all of these vectors in this situation All right, where we fill it with all the A vectors. A1, A2, so on, AP. And then this is an augmented matrix, so we also put in B. Okay. When reduced to echelon form, doesn't have to be reduced, just echelon form. Okay. All right, so either a row has a pivot position, like these first two rows here, or if a row is entirely zero, including the part of the right-hand side, because that's the same way as how we identify a system as consistent. So all of these mean the same thing. So if you're given a problem where you're asked, is this vector a linear combination of these, or is this vector in the span of these given vectors, then you just put together the augmented matrix, go ahead and row reduce it, and depending on whether you get a consistent system or not, that gives you the answer to this question. So in certain problems, and that's what I've seen in this week's assignments, you may actually be performing the same kind of manipulations to answer questions that appear to be different. And sure enough, here we have the same kind of situation. Here we have this given vector, and you're asked, is this a linear combination of these vectors that are the columns of this matrix? Okay, and like I was saying earlier, so this vector is a linear combination of these. In other words, B is in the span of them, if and only if this system is consistent. So what you can do is I can just take this vector B, slap it onto here as a fourth column, and then just like in the previous problem, work with this augmented matrix. So to eliminate elements, I'm going to take -3 times this row to make these elements agree, and then I can subtract. So that's the same way as saying third row is equal to itself plus 3 times this row. And we end up with this. But this is a bad thing to have happen to an augmented matrix because, so I wanted each row to have a pivot position or be entirely zero, but this row is not. We actually have an equation 0 equals 16 that has no solution. So in other words, the system is this example of an inconsistent system. So when it happens, we say that B is not a linear combination of these vectors. But we cannot find scalars x1, x2, x3 that you can multiply these vectors by and add them up to get B. So these last two problems give you a good indication of what does a consistent or inconsistent system look like. So you can see the contrast there. So here we have no solution. The previous one had infinitely many solutions because of the row that's entirely zero. All right. Now, here we have two given vectors. And the question is, how would we geometrically describe the span of all of these vectors? So what does it mean to have, so a linear combination of these two vectors, what would that look like? Now, generally, if you have two vectors like this in 3 dimensions, and you take any linear combination of them, or like a set of all possible linear combinations, normally that would give you a plane. So a 2-dimensional plane embedded within 3-dimensional space. But that does not happen in this case. Okay, so here we have formal definition of span. All right, again, it's a set of all possible linear combinations. And this is a nod to another problem in this section. Remember, these numbers, C1, C2 up to CP, they are allowed to be anything. Span covers all possible linear combinations. There's no restriction of these, like, they're allowed to be 0, for instance. They could be any real number whatsoever. So what that means is I could choose all of these coefficients, C1, C2 up to CP. I could choose them all 0. And what I get, therefore, will be the 0 vector. So the span of any set of vectors will include the 0 vector. And so here when we have a set of a linear combination of vectors equal to some given vector B, and this gets to the equivalent statements I wrote typed out earlier. If this system has a solution, B is in the span of these vectors because B is a linear combination of them. Okay. Now, with regard to these two vectors here, one thing to look for is, are these two vectors parallel? The way you can tell is if you look at the ratio of these elements, so 20 divided by 8, 10 divided by 4, 5 minus 5 divided by minus 2, the ratio is the same, 5 halves. So this vector is equal to 5 halves times this vector. So what we can say, so V1 is a scalar multiple of V2 or vice versa. So those vectors are parallel. So what that means is the span is not a plane in this case. So if I picked out two arbitrary vectors in 3-dimensional space, generally they would give you a plane. But really it's all multiples of V1 because I could take multiples of V1 and multiples of V2 and add them together. But V1 is a multiple of V2. So in other words, this vector is redundant. It's this vector. You can pick either one of these vectors and describe everything it's in the span. So it's all multiples of V1. But if you take a single vector like this V1 and look at all possible multiples, they sit on a line. So, so if you look at a line that basically has V1 as its direction, so it starts at the origin and points in the direction of V1. If I multiply this by anything, I'm going to get a point somewhere along that line. So the span of one vector gives you a line. The span of two vectors gives you a plane unless the two vectors are parallel. So that's the thing to check for. To understand the span of two given vectors, check if they're parallel first. All right, here I have two given vectors, and I have an unknown vector xy. So this is any vector in 2-dimensional space. So I want to show that this vector can be expressed as a linear combination of these two, no matter what xy is. So for that, I need this vector to be equal to a constant times this vector plus a constant times this one. All right. So I need AU plus BV to be equal to XY. But then I write out what this is. So it's A times this vector plus B times this vector. So if I distribute the A and B through their respective vectors, I get this. So I've written this vector equation as a system of equations. So I want to see if this system of equations has a solution, A and B. I'm going to move this onto another page. Okay. So what's the augmented matrix for this system? Right. So it's the coefficients of A, one column, coefficients of B in the second column, and then X and Y. So now I need to work with this augmented matrix and perform row reduction to see if the system is consistent or not. So row 2 would be equal to itself plus this row divided by 15 to eliminate this -1 down here. And this is what I get. So there's no more reduction to be done. This is an echelon form. And every row has a pivot position. There are no rows that are entirely zero. So this system is consistent. So we don't have a situation like what came up in the previous problem. So every row has a pivot element. When every row has a pivot element, that implies that there's a unique solution. Wait. Only if the number of rows is the same as the number of columns. Okay. So I'll make a note of that here. Okay, well, first I want to mention this also. Yeah, so here we'd have infinitely many solutions, but so the solution is unique if and so the coefficient matrix is a square matrix. All right, so same number of rows and columns. All right, so I could be a little more general here. Every column has a pivot element. So this covers a case where there are more rows than columns. I mean, you also have unique solutions. So, for example, suppose I have a system of equations, and this came up one of the problems from last week. Say 3 rows, 3 equations, 2 unknowns. So your coefficient matrix is 3 rows, 2 columns, 3 by 2. So that's called an overdetermined system. You have too many equations for the number of unknowns that you have. So, but if you go ahead and row reduce a matrix and you find that both columns, first and second column, have a pivot element, so there's no free variable, and you also get like a third row being entirely zero, so right hand side included, that system has a unique solution. Whereas if you have a situation where you have any free variables, that's infinitely many solutions. All right, now for this problem, I have a word problem now and then. Okay, so here we have an application problem that leads to a system of linear equations. So what we're given is how much is of copper and silver that is produced by two different mines. These vectors describe the daily production of each mine. So first element refers to how many tons of copper. Second element refers to how many kilograms of silver. So this describes the daily production of a first mine, mine number 1. This describes the daily production of mine number 2. Okay. Now, there's two parts to this. The first part is what is the physical interpretation? If I take this vector multiplied by 4, what does that mean? That's how much is produced by mine number 1 after 4 days, because the vector itself describes 1 day's production. So we just multiply it by any scalar to get the production over that many days, whatever the scalar is. Okay. Now, all right, so suppose we're running these mines for different lengths of time. So x1 days for this mine, x2 days for this mine. Now, what we want to do is set up a system of equations where we find the right combination of production cycles for each mine. Like how many days do we want to run this mine for and this mine for to get a certain amount, an exact amount of copper and silver. So the idea is I want to run this mine for x1 days and this mine for x2 days, see what the total production of both mines is, add them together, and this is what I want to get. So if these mines are giving this fixed amount of output for however many days I run, for each day that I run, how many days will it take running it to get this combination of output? So then we go ahead and solve this equation. So what I could do is I can write out, I can fill in what V1 and V2 are as a system of equations. So here I have this vector times x1, so that's a 20 and 530. This vector times x2, so that gives you a 30 and 500, and must be equal to this. So then I could just read off of this the augmented matrix. So then I go ahead and carry out row operations. So I want to take this row and subtract from it this row, multiply by 530, divide by 20, and that is what it gets subtracted. And since this is just a system of two equations, that's all it's going to take to get to echelon form. So now I can solve this system because it's an echelon form. So for instance, for x2, you can solve for that first. I just take this divided by x2's coefficient, and I get 2.3. So that tells me that mine number 2 should run for 2.3 days. Then I can take that value of x2 and substitute it back up here into this equation, and that's where I get this, and I rearrange it to get x1. So I rearrange this equation to isolate x1, substituted my known value of x2, and I find that x1 is equal to 2. So that tells me that, so if you run my number 1 for 2 days, my number 2 for 2.3 days, the total production from the mines over those periods of time will be exactly 109 tons of copper and 2210 kilograms of silver. Does anyone have any questions about the problems presented here? Or about the homework problems from the sections assigned last week? But take a look at the first assignment. I'm checking on how many have completed it. Not everybody, but certainly the majority. Oh, wait. Oh, that gives me the overall. It doesn't break it down by assignment. Okay, well, certainly a clear majority have finished homework 1. Good. So the rest of you who have not finished homework 1, but you are currently here, you're going to be able to finish those without any difficulty, and if not, there should be some questions. We also have a second assignment due on Thursday. Which, okay, a handful of you have completed. Okay, I will end the recording. Any of you has questions, or I'll stick around until everybody's gone, or until 3:45, whichever comes first. So until Wednesday.